Before we dig deeper into the new attacks, let's recap what we thought the threats were. Until IDESaster came to light, security researchers and developers did know about some vulnerabilities in AI coding assistance, but they all focused on the AI layer itself, not the underlying IDE. This slide likely sketches out that public threat model, basically the known ways to attack AI in IDEs prior to this research. So what did that include? 3 main components: prompt injection, AI brain hacks, vulnerable AI tools functions, AI agent settings configuration. So let's understand prompt injection. This is where an attacker sneaks malicious instructions into the AI's input, the prompt or context. We knew that large language models can be jailbroken or tricked into ignoring rules. So if an attacker could plant some hidden command in code, like in a comment or a data file, the AI might pick it up and follow it. That's context hijacking. The AI does something the attacker wants because it was in the input. Now, vulnerable AI tools or functions. AI agents use tools like file readers, web fetchers, or terminal commands to act on our behalf. The known threat model considered that some of those tools might themselves be insecure. For example, a code generation AI might have an execute shell command tool that had a vulnerability, say it didn't sanitize input leading to command injection. Attackers could exploit that to break out of the intended constraints. We saw real examples of this. For example, a mermaid diagram plugin that allowed data theft, or a shell execution tool that could be tricked into running arbitrary commands. Now next, AI agent settings or configuration. Another known angle was the AI's own configuration files or settings. In some AI IDE plugins, the agent settings, like whether it requires user approval to run code, were stored in files that the agent could edit. If an attacker got the AI to edit those, it could turn off safety measures. Public exploits showed agents editing VS Code settings to auto-approve dangerous actions or modifying a configuration to grant itself more autonomy. Essentially, the AI could rewrite its own rules if not properly protected. So, all the publicly disclosed attacks up to now fell into the chains like prompt injection, vulnerable tool. AI gets bad input, uses a buggy tool, and causes harm. Prompt injection, legit tools, AI agent settings. AI gets bad input, uses normal tools to edit its configuration, causes harm. Prompt injection, vulnerable tool, settings. AI gets bad input, uses a buggy tool to directly alter settings. This slide probably illustrates these chains and maybe lists examples. The important thing here is all these known attacks, they assumed the battle was confined to the AI's domain. The model, its tools, its configuration. The base IDE like VS Code itself or JetBrains' IntelliJ platform was considered out of scope and almost neutral ground. From a security practitioner's view, this wasn't foolish. It was just based on known information. We patch the specific plugin or sandbox the tool and we think we've secured the AI integration. From a legal standpoint, one could argue that vendors who address these known issues were meeting the standard of care as it was understood. But this is the turning point. That threat model had a fatal blind spot, which IDESaster now exposes. We were so busy watching the AI that we took the IDE for granted. That sets the stage for the next slide, what everyone missed. And now here's the aha moment. We left the back door open. The AI IDE threat model had a critical blind spot, the base IDE's own features. This slide likely shows how our focus on the AI agent and its tools made us overlook the foundation everything runs on. The AI IDEs effectively ignored the base IDE software in their threat models, assuming it was inherently safe after years of use. That assumption no longer holds. Once you let an AI agent act autonomously inside an IDE, all those safe legacy features can be weaponized for malicious ends. In essence, the base IDE's features must now be considered part of the attack surface. Think about what that means. Modern IDEs like VS Code, JetBrains IDEs, etc., They are complex beasts with tons of functionality. File system watchers, task runners, debuggers, formatting tools, extensions, you name it. These were built for developers' productivity, not with a hostile AI in mind. Under normal use, a developer leverages these features consciously, but an AI agent can trigger them or manipulate them faster and in combinations a human might never consider, and do so on attacker-provided instructions. This slide might depict this as an expanded threat model diagram. Previously, we had AI and tools. Now we add base IDE to the chain. For example, a note might say, base IDE features should be an integral part of the threat model now. That's directly from the research. It's almost a warning to all of us. Don't trust the ground you're standing on if you've added AI to it without re-inspecting it. From a security perspective, acknowledging this blind spot means we have to re-audit all those boring IDE features in the context of AI. Features like auto-fetching resources, auto-building code, or synchronizing settings, could an AI abuse those? As we see in the case studies, yes, it absolutely can. From a legal and responsibility angle, this raises tough questions. If a vendor failed to include the base IDE in their threat model and a breach occurred through it, was that negligence? We're exploring new territory. Historically, if you extend a software with a plugin, you're expected to consider how that plugin could introduce vulnerabilities. Here, the plugin is the AI agent, and it turns out it can impact the core software. One might argue that now this blind spot is known. Any vendor continuing to add AI into their IDE without addressing base features could be seen as negligent. Regulators and industry standards may start insisting, did you consider how your base systems interacts with AI? If not, that's a compliance gap. The key point of this slide, the base IDE is not off limits to attackers. In fact, it's the new playground. We have to update our security thinking to cover this, which leads directly into the new class of attacks, the IDESaster chain. Now, for the main event, what exactly is the IDESaster attack chain? This slide introduces the novel exploit chain that defines the IDESaster class, prompt injections, tools, base IDE features. It's the culmination of everything we've been building up. An attacker uses the AI to activate underlying IDE functionality to do something bad. So now let's break it down. Prompt injection, I've covered in my last video. The attack still often starts with the classic trick, getting malicious instructions into the AI's input. As we said, this can happen via a poisoned file, a sneaky comment, etc. It's nearly inevitable that given enough creativity, an attacker can inject something. The researcher even notes it's inevitable this will eventually happen one way or another. Now, tools. The AI, following those injected instructions, uses whatever tools or functions it has at its disposal inside the IDE. This could be a file writer, a web fetcher, a terminal command executor, etc. Importantly, these tools might not themselves be flawed. The AI could be using legitimate capabilities like write file exactly as intended. Now, base IDE features. Here's the twist. The AI's action with those tools are aimed at triggering some base IDE feature that was not previously in play. For instance, writing a specifically crafted file that the IDE will automatically process as feature, or editing a configuration that the IDE will automatically apply, leading to execution of code. The final impact can be anything from information leakage to full remote code execution depending on the feature abused. This chain is universal in the sense that it doesn't rely on a specific bug in one AI product's code. It leverages the shared behaviors of underlying platform. The researcher highlighted that this is application agnostic. Any AI IDE using the same base platform, VS Code, JetBrains, etc., likely inherited the vulnerability. That's why when one base IDE, say VS Code, has a weakness, dozens of AI tools built on it were all vulnerable in similar ways. The novelty here cannot be overstated. In cybersecurity, we rarely see a new category of attack that cuts across products. This is like when SQL injection was first discovered on websites. Suddenly, a whole class of applications had to worry about it. IDESaster is that kind of class for AI IDEs. For the audience of AI developers and tool vendors, the immediate implication is: don't just test your AI plugin in isolation. Examine what base IDE features it could indirectly trigger. Threat modeling needs to expand. For policymakers and legal experts, it's a case study in systemic risk. When vulnerabilities are so pervasive across any products and vendors, it might not be enough to leave it to each company to handle quietly. It might call for a coordinated response, maybe an industry consortium for secure AI tools or alerts for agencies like CISA, Cybersecurity and Infrastructure Security Agency, to raise awareness. We might even see pressure for supply chain security audits for development tools used in critical industries. For example, if a bank's developers use an AI tool, regulators might ask, have you accounted for these IDESaster type risks? If not, they should. So the slide's simple message: here is the new attack paradigm. It's broad, it's powerful, and it requires us to all update our defenses. Next, we'll see exactly how it plays out in real examples.